Next, and I'm not sure why his picture just disappeared on my slide, but I'd like to welcome Dr. Dan Williams, the Director of Commercial Vehicle, ADAS, and Autonomy at ZF Group, to the stage. Dan is going to be our guest speaker for the August 2021 segment. We've titled it Meet an Expert on Vehicle Dynamics. Welcome, Dan.
Hi.
Yes.
Hi,
yes,
I hope you can hear
great.
me.
Your background looks really nice as well. Much warmer and sunnier than where I'm at.
Yeah, I guess there's advantages to working in the time of COVID. I had a choice between going into the office where with the Delta variant, we've got to wear masks even if you're vaccinated, and in a largely vacant office space. So
yeah,
decided to come out here.
Thank you again for volunteering your time to join us today. Now, I understand you have a couple slides that you're going to review with us, and then I have a bunch of questions for you, if that's okay.
Sure, that's fine. Do you have those
Yeah,
slides?
they're up on the screen
Angela?
now. It's like, yeah, the ride section
Okay.
we're going to start with.
Okay, got it. Yeah, so what I thought we could do is just kind of go through chapter by chapter real quick how this book kind of flows, and everybody can get an idea of what we're trying to cover here. Like a lot of vehicle dynamics books, we kind of separate things into ride and handling. We start the book with a ride section, and we start with a kind of historical perspective. I mean, I think that's something that you'll see as sort of a common thread through all this, is an appreciation of the history of the field. And then we move into sort of a chapter that has a couple different purposes. We introduce a simple mass suspended on a stiffness. It's an example of kind of the simplest linear system you can imagine. So we kind of use that as an example to introduce a lot of the analysis methods and tools that we're going to use throughout the book. And also it kind of is it's a simple model of a vehicle sitting on the composite stiffnesses. So it introduces sort of a vibration in the vertical or the heave mode. And then in the next chapter, the quarter car model, we introduce one of the most fundamental vehicle dynamic models, where in addition to the mass on top of this stiffness, that would be the sprung mass, we introduce another mass that is located by the tire stiffness and then the suspension stiffness. And with these two masses, we're able to talk about two different resonant modes, the wheel hop mode and the ride mode, two things that are just fundamental to vehicle dynamics. One of the things that we do a little bit different in this book is we derive these equations in transient form. And so when we do that, we can look at these at the ride natural frequency and the wheel hop natural frequency, and we can see that they're actually coupled in the equations. And then we can make the assumptions that are typically made that that show how the ride frequency is really the mass sitting on the series combination of the suspension and the tire spring, and conversely the wheel hop frequency is the unsprung mass in the parallel combination of those springs. So we kind of derive the general case, and then we show with these assumptions how these specific resonances can have some physical sense. We also present this thing called the isolation function that allows us to kind of visualize the results a little bit better and show some trade-offs in the parameter suspension, or the suspension parameter sensitivity. Then in addition to the heave mode, we add the pitch mode, and that introduces this pitch plane model. That's something that has been described for a long time by one of the giants of the field, Maurice Olley. He did develop this ride criteria. We talk about that, and then one thing that's kind of neat that we do is we can show that for a 3-axle model, the Olley ride criteria actually gives us kind of a unique solution, whereas before it's kind of an over-constrained solution, and there's some design that has to be done. Then we move on to the roll plane model. That's kind of an interesting chapter in this work. You don't always see roll plane in ride, and the reason that we put in here is really a couple different reasons. One is we can talk about the effect of a stabilizer bar, which is a good way to kind of get around some of the inherent compromises in ride. When you talk about the stabilizer bar, it allows you to talk about the effect of roll moment distribution on handling. And also it allows you to talk about kind of the trade-off between roll stiffness and single wheel stiffness in response to single wheel events. And both of those things are very interesting for this last chapter on active suspension. What we've tried to do in the book is have capstone chapters that kind of bring all the concepts that we talk about in the various sections together. We use active suspension for that in this book, and we talk about the combination of heave, ride, and roll. And we're able to kind of bring together some of the early strands of active suspension research, the stuff that was done at Lotus that I'm pretty familiar with, and the stuff that was done on skyhook damping. We show how these two independent sort of developments of active suspension can be brought together and result in a really a vehicle that has unprecedented ride and handling. And this is an actual vehicle where we've brought these sort of concepts together. So then we move on in the second part of the book to handling, and we start off with a chapter on handling basics. And again, this development is kind of following a series of lectures that I did for a graduate class at Purdue University. We talk about some pretty basic things of steering kinematics, Ackerman steering. And then in this chapter, we also use steering compliance to introduce sort of the concept of understeer. I think it's important that people get kind of an intuitive feel for things like understeer, and I think it works well to just kind of for the person to visualize that as compliance in the steering system. And then we do something that's maybe a little bit different in a lot of vehicle dynamics texts. We sort of formally define reference frames. And that's important because we're eventually going to touch on things like a rolling sprung mass, and you've got to be careful with how you define things. So we do a formal chapter on that. And then this next chapter is perhaps the most important chapter in the book. We change some conventions that are typically used in vehicle dynamics. We change the slip angle convention. We actually use the opposite of slip angles. We call it attack angles. Then we also change the way that axles are located in these various models. And then we derive the two-axle yaw plane model. A lot of people call that the bicycle model. That's probably the second fundamental vehicle dynamic model. And one of the things that we see when we do the block diagram of the two-axle yaw plane model, we can really appreciate the effect of these changes in conventions that we've used as we compare that with a more conventional bicycle model. Then from there, we go in kind of three different directions in the next three chapters. The first direction we go is we add rear axle steer to that two-axle yaw plane model. We include a pretty simple driver model, and we use the combination of that driver model and the vehicle and lane keeping to be able to derive a rear axle control law that kind of shapes the open loop of that rear axle steering system. And then we add roll. This is something that is not too commonly done in vehicle dynamics texts. It is done in an out-of-print text by J.R. Ellis, and that's one of my favorite vehicle dynamics texts. And basically, this chapter just kind of mirrors what Ellis did, only with these new conventions. And then in the third of these three different directions that we go is we actually add a third axle to the two-axle system. And you can see that these new conventions basically make it a very easy thing to add that third axle, much easier than if any of you are familiar in the literature of how that's done. And then we take that a step further in the next chapter, and we show how you can add really any number of axles, any of them steered, into a rolling vehicle model. And then just like the first section, we close this section with kind of a capstone chapter where we try to pull everything together that we've used. We describe work done on an actual vehicle where we use rear axle steer to serve as steering redundancy in the event that the primary front axle steer fails on perhaps an autonomous vehicle. So Angela, that's kind of a quick flyby on what we've got in the book.
Yeah,
so with that,
no,
maybe I
really
can answer any questions for you.
Through that, and kind of breaking down what's different as well in lieu of a generalized vehicle dynamics book. So somebody in the audience asked a very similar question that I was going to ask you. With so many vehicle dynamics books out there, what inspired you to write this new one? And the question that's sort of related to that as well was, what added value does this book have compared to Gillespie's book, that book's vehicle dynamics? Yours is generalized vehicle dynamics.
Well, that's a great question, and this book, I think, really complements the book that Tom Gillespie has done and has recently been reissued. What we've done in this book is there's really two things that I think are kind of unique in the whole sort of constellation of vehicle dynamics books. One is we do a little bit more, I guess you'd say, formal development of the equations. There's a lot of vehicle dynamics books that you'd be hard pressed to find a differential equation in a book with dynamics in the title, which sort of gives you sort of a layman's, I guess, definition of dynamics where they're really talking about motion. But we really talk about dynamics in the formal sense, where dynamics are a change in motion. We derive these equations from first principles, and we get a lot of sort of transient models of these different modes of vehicle motion. And then we'll go back and we'll solve these transient models in steady state and come up with some of the more familiar sort of notions of understeer and wheelbase and things like that. So, one of the first things that I think makes this book particularly sort of interesting is the formal development that we do. An example of that is the reference frame chapter that we've talked about, where we go through and kind of formally define all these rotating reference frames. And when you do that, you kind of see a lot of the implicit assumptions in things like the bicycle model that a lot of people have probably just taken for granted. There's a lot of symmetry that's assumed in the bicycle model that make all of the kind of co-products of inertia of the sprung mass kind of disappear and allow you to write this relatively simple acceleration term for the bicycle model. If you formally derive that, you can see these assumptions and you can understand them better. And another reason why we like to do the formal analysis, formal derivation of the reference frames is it allows us to eventually add things like a rolling sprung mass, which are a little bit, you just have to be more careful in how you define the reference frames when you do that. So the one thing I would say that makes this text unique, and it's not completely unique because Ellis certainly did that in his out of print book, but we formally define a lot of these reference frames and equations. We use kind of a control theory background. So we talk about things like resonances. We use tools like Laplace transforms and block diagrams. So hopefully that doesn't scare too many people away. That's what we use. The first chapter of this is like a refresher course. So anybody that's had kind of the first undergraduate semester class in linear dynamic systems or control theory is going to read that first chapter. And I think we're going to be able to kind of remind you of a lot of the things that you've learned in that class, and you'll be just fine in this book. And then we use kind of those control theory tools to develop a lot of the concepts that we talk about. And then the final thing that I think makes this book unique is that because we use this kind of generalized approach, and we can talk about the Ollie ride criteria for a vehicle that has any number of axles in it. And similarly with the bicycle model, we can talk about a bicycle model that has any number of axles, any of them steered. And we use the two-axle passenger car, kind of the most common passenger car model of a front axle steered passenger car, as a special case of this more generalized model that can encompass really all different vehicles that you can imagine. And you can imagine that generalized model is more applicable to commercial vehicles. So I would say, to summarize that kind of long-winded answer, the two things that make it unique are the kind of applicability to commercial vehicles and the control systems background. I think it would be a good book for a lot of people that have kind of a control systems background, that are maybe wanting to get into vehicle dynamics, that haven't had a vehicle dynamics class in university. And I think there's probably a few people that are starting to look at vehicle dynamics in the context of autonomous vehicles that probably fall into that.
So that was
category.
my next question. Who should read this book and how is it applied to current projects? So I think you can kind of answer that. Do you have any elaboration on that?
No, I would just, I guess, reiterate that, I think it's a good general book for anybody that's got an interest in vehicle dynamics that maybe goes a little bit, beyond Tom Gillespie's book. In fact, when I taught the class at Purdue, I used Tom's book as kind of as a prerequisite to get everybody up to speed on kind of the fundamentals of vehicle dynamics, which I think is actually the title of his book. This kind of goes a step further, uses some control theory techniques, looks at some things in a little bit more detail, like rear axle steer, vehicles that roll, multi-axle vehicles, things like that, in a control systems kind of context.
So my next question was, how does this book tie into your current role at ZF Group?
Well, it's largely a product, I wouldn't say necessarily of my current position, but certainly of my history with ZF. The first probably third of my career, kind of mirrors the first third of this book in RIDE. I worked on passenger car active suspension. And in fact, the capstone chapter that we present in this book is kind of a Reader's Digest version of a paper I did for ASME on active suspension. And actually that paper, it was a ASME lecture on active suspension that was actually written up in the SAE Journal of Vibration and Control or something like that. And then the second part on handling was really kind of motivated by what I did after that, when I started thinking about things like vehicle dynamic handling of 3-axle vehicles, and looking at things like rear axle steer for 3-axle vehicles and that sort of thing. And that really led to the capstone chapter of the second part of the book. So I think the complete experience with my career at ZF has kind of provided some real world examples that we can apply all of this, somewhat occasionally esoteric theory to.
So I was talking to Sherry Nagam, that's our publisher for SAE Books. That's who you've been working with. And she said that you asked for a Tyrrell P34 on the cover. For those like myself who may not know, could you describe what makes that vehicle so unique?
Oh, sure. I mean, there's a lot behind that particular vehicle. For those in the audience that might be Formula One aficionados, you know that Tyrrell drove a 6-wheeled 3-axle vehicle in the mid-70s. For those of you that might have seen the recent movie, it's a great movie called Rush, that talked about kind of the driver duel in 1976 between Niki Lauda and James Hunt. You'll see that this vehicle kind of makes a cameo appearance. It looks like this just really weird vehicle that is shown occasionally in some of the racing shots for that really good movie. And by the way, I'd recommend that movie to anybody. If those of you that are engineers and like F1, Niki Lauda is probably one of our heroes. He wrote a book on kind of, I think it was called something like The Art and Science of Formula One Racing. Great book. I quote from that book in my book. But kind of hidden below that sort of major plot line of the driver duel between James Hunt and Niki Lauda was this Tyrrell that was driven for 2 years. It actually won the Swedish Grand Prix in that very year when Lauda and Hunt were dueling for the Drivers' Championship. The Tyrrell got first and second in the Swedish Grand Prix, and Tyrrell finished third in the Constructors' Cup that year with this very weird design. And they actually didn't even have this design ready for the first few races of that year. So, it did really well. And the reason that I wanted to show that on the cover is a lot of people would think, and rightly so, that multi-axle vehicles have particular application to commercial vehicles. And they do, no doubt about that. That's how I got into it. But they also have application to these other, kind of specialty vehicles like the Tyrrell P34. So I really like that she was able to find that picture. I love it.
Okay, very cool. So my next questions were more kind of shifting from the book and about kind of the current technological landscape of vehicle dynamics. Before we do that, Kevin asked, Dan refers to we often when you were talking about collaborating on the book. Who were the other authors or contributors you worked with to pull this together?
Well, that's just kind of a habit of mine of using we, I guess, rather than I. I've written the book, but to list the other, collaborators, I mean, I've had a whole career worth of collaborators. There was a guy that I worked with for quite a few years that has now moved on to a different company, Amin Neela. Amin did his PhD at Purdue, and we collaborated on a lot of this work. And the final capstone chapter on 3-axle vehicle dynamics borrows a lot from the work that that Amin and I did. There's a number of other people within ZF and TRW that that I worked with. I as far as kind of the people from sort of an academic side that I've borrowed from, Dan Metz from the University of Illinois kind of got me started on vehicle dynamics. I mentioned the J.R. Ellis book that I just love, and you know, I would consider this book to be kind of a newer sort of follow-on expanded version of his just fantastic book. Yeah, so yeah, I guess I shouldn't say we as much, but
you've had
that's just my habit.
Yeah, influence from other areas. Yeah.
Yeah, for sure,
Dan,
for sure.
You mentioned ride and handling sections of your new book. How about other sections of vehicle dynamics? You foresee any others?
Well, yeah, I mean, when I sat down and started plotting this out, you know, I thought that the book would perhaps cover a lot more than it did. I mean, we completely leave out the longitudinal degrees of freedom. That introduces brakes, it introduces powertrain and transmission and that sort of thing. That's something that was actually touched on in my Purdue class, but I didn't think that my contributions were as unique in that field. That was kind of more just exposing the students to stuff that other people had done. So I had intended to include some kind of survey chapters on that, but the book just got to be too big, you know, as it was going on. I really, as I started teaching that Purdue class, I got into some more sort of aerodynamic topics that I really hadn't appreciated before in my sort of chassis control work. And I found those to be fascinating. I really wanted to include aero, and you could really have included a chapter on handling with sort of side forces generated by aerodynamics that would be very interesting and also kind of relevant to commercial vehicles particularly. But you know, the book just was too big. And then there's the whole topic of articulated vehicles, which I wanted to include because that's, again, a topic that is particularly relevant to commercial vehicles. But again, I mean, we've had to really kind of be careful with how big the book has gotten just with the current topics that are covered. So there
Maybe
are definitely things that have been left on the table.
Books. Okay, so Sven had a question that I wanted to set up as well, because it kind of led into my next one for you. What has changed in vehicle dynamics since the beginning of your career? And Sven's question kind of, you know, sets up for that. Are there any new trends in tire models that Dan might want to point us to? So what's changed in vehicle dynamics since you started? And then Sven's question about trends in tire models.
Well, let me answer the second question first, because I think that's probably the shortest answer. You know, I talked about how we use Laplace transforms and block diagram algebra in this book. Those basically assume linear systems. And so we've had to make kind of the typical assumptions about linear tires. That's why this convention between attack angles and slip angles is so important. You know, there are definitely more sort of tire models. If you're actually trying to use this work to predict actual vehicle performance, there's lots of places where you see those. Pacheco's book on tire models is the classic, you know, that I would refer anybody to. We do touch on the nonlinear tire behavior in terms of roll moment distribution, but that kind of gets into why we did that in the roll mode chapter of the ride section, because it is kind of a nonlinear effect. And when we talk about handling and the handling effects of the roll mode, those are all kind of linear tire behavior. So we really used a relatively simple model because we have to, because most of what we talk about is a linear system. in terms of how vehicle dynamics change, I mean, that's something that I'm really excited about. Say 20 years ago, when I first started working in the commercial vehicle field, the commercial vehicle engineering groups were just dominated by concerns of cost and quality and emissions and fuel economy. In fact, in commercial vehicles, it seemed like back in those days, just as soon as we got done addressing the needs of one emission standard, the next one was coming down the pipe, and we had to start, and many times, had to start figuring out how we were going to deal with the next one before we even got the full one completely implemented. And and sometimes these implementations, as you guys know, with the after treatment and that sort of thing on commercial vehicles, I mean, it makes a huge impact on the vehicles. So that was just eating up all of the engineering resources that were out there. So with the advent of ADAS and particularly autonomous driving, now all of a sudden, the OEM customers are looking to vehicle dynamics as real sources of value. You guys might have run across a great book that Larry Burns did a couple years ago. I think it was called Autonomy. And he basically identifies how autonomous technology converges with electric propulsion and ride sharing to create this like perfect storm of just extreme synergy, and he's calculated just enormous value that this confluence of these three effects can create. And I think that opens up just all kinds of opportunities for people in vehicle dynamics. A good example of that is active suspension, where I spent, as I said, the first third of my career. I talked about how cost and quality and emissions and fuel economy were most important. Really active suspension probably hurts you in all four of those. You could make that argument. And it really increases functionality, but it really hurts you in the four things that were the most important in those days. And now we see with the advent of autonomous vehicles, there's some speculation that something like 20% of the population that is not driving, that is riding in a car like everybody would in an autonomous vehicle, 20% of people that ride in cars get car sick. And that can be solved through active suspension. So all of a sudden, active suspension, it doesn't just take away from, cost and quality and fuel economy and that sort of thing, but it enables all the rest of the value that you get from this confluence of all these really powerful trends that come together in autonomous vehicles. So, and I think to tie that maybe in with the other capstone chapter that I do, one of the things that I'm probably the most excited about is how autonomous vehicles can actually change how vehicles look. In the last chapter, we looked at how you could take rear axle steer and use that as redundancy in the event of failure of the primary axle steering. But we also go a step further and say, okay, now if you're actually steering the rear axle, you can change the layout of the vehicle. You can move the second axle, which now has to be close to the third axle to reduce tire scrub and to improve vehicle maneuverability. You can move that second axle to the middle of the vehicle. You can carry more load based on most load regulations in different states and that sort of thing. The vehicle can be more maneuverable, and you still have the redundancy that you need for the primary front axle steering. And so, if you can imagine, that's going to change the look of a lot of these three axle vehicles if something like that would happen. Once you take kind of the human control element out of the vehicle architecture and you go with more sort of redundant computer control systems to assume that human control constraint, I think it just would boggle the imagination, to try to contemplate how vehicles are going to change, after autonomous vehicles are implemented.
Yeah, really good points.
And that's going to be exciting for us.
Yeah, thank you for that explanation. We have time for one last question, and it's from Emmanuel. He asks, do you have problem set examples for readers in the book that can be implemented in software environments, such as MATLAB and Simulink?
That's a good question. We really don't have well, I shouldn't say that. There are some examples. We use they're not really formal examples and they're not really formal problems, but we kind of work through, for example, when we talk about these like, well, I think I talked about earlier, the ride frequency and the wheel hop frequency. We'll throw in typical parameters and we'll find the exact solution of these coupled natural frequencies. And then we'll go through and look at the sort of assumptions that make these solutions decoupled into a particular ride frequency and a particular wheel hop frequency. And using these typical parameters, we can show the agreement between the two. We do that at a couple different times in the context of the book, and then I'd say in the 2 capstone chapters, that's when we really look at the actual vehicle behavior, and we look at applying these techniques to actual vehicles. So there's not really the kind of, as you might expect at the end of a chapter, a problem set, or within the chapter specific examples that have been worked out. But we do try to use real vehicle parameters to illustrate our points, and we try to, in these capstone chapters, show how all of these concepts can be directly applied to real vehicles.
All right, thank you. So those are all the questions in the chat window. Dan, we do have to move on to our next section, but I thank you so much for volunteering your time today and all of your in-depth explanations about your new book. It's publishing later this year, right?
Well, I think it might be in the process of being slid to early next year, but somewhere in there, late this year, early next year. What we'd really like to get it out in time for World Congress.
So
that's really kind of the goal.
Whenever we do our segment for WCX next year, I think that's happening in April. We'll definitely make sure we circle back and highlight your book publication. Congratulations. Hopefully you have some new titles to work on with Sherry as well to include those other chapters. All right. Well, thank you so much, Dan. Really appreciate your time. Yeah, absolutely. So for everybody joining today, and I apologize, of course, I'm starting to lose my voice.